All right, I'm going to show you complex exponentials today. Complex exponentials are an amazing mathematical tool that can take difficult things and make them simple, and take impossible problems and make them possible. All right, but first we have to master complex exponentials before we can use them. So a complex exponential is just e to the I something, right? So I take e to the I theta, and I plug some real value of theta in. It turns out what I get back is a complex number. And it turns out what you get is cosine of theta plus I sine of theta. This is known as Euler's formula. All right? If you want to prove that it's true, you can use a Taylor series. It's not hard. Do a Taylor series of this, do a Taylor series of this, and a Taylor series of this, and you'll see that you add these two together and you get that one, and you've got your proof. All right? And you can kind of see what's going to happen. You take derivatives of an exponential, and all you do is you get the I out front every time you do your derivative. All right? So you get all the terms in your Taylor series. With cosine, you're only going to get the even powers of theta. With sine, you're only going to get to odd. When you combine them together, you'll get this. Anyway, why is Euler's formula useful? Well, because sines and cosines are really important in physics. You may have noticed that. They show up everywhere. You do the harmonic oscillator, you get things that oscillate sinusoidally. And it turns out harmonic oscillators are everywhere. You take some system, displace it from equilibrium by some small amount, it tends to oscillate harmonically. It shows up when we talk about guitar strings, and when we talk about sound waves and air, and so forth. So sine waves are fundamental to physics, but they can be kind of a pain to work with. For example, imagine you had a wave described as sine of omega t plus phi. You've got this oscillating, this time-dependent part, but then you've got the static term right here. It'd be nice if you could separate them, right? Or maybe I have to add two sine waves together with a different phase shift, right? That can be a real pain. But exponentials are easy. If I have e to the I omega t plus phi, I can just separate those two. I can write that as e to the I omega times e to the I phi, right? Exponentials, I know what to do with. They're a lot easier to work with. So Euler's formula allows us to take things that normally we would use sines and cosines for, and instead use an exponential, which makes things easier. Okay, now what do you get if you plug some real theta into this equation? The real part goes as cosine of theta, the imaginary part goes as sine of theta, so it turns out it traces a circle in the complex plane. So if I take e to the 0, e to the I 0, that's just e to the 0, and that's just 1, right? So that's this point, this blue spot on the complex plane. But if I plug in theta equals pi over 20, you get this on the complex plane. If I keep incrementing theta by pi over 20 and plotting the points on the complex plane, it just traces out a circle in the complex plane. All right? So what does that tell us? If I take the magnitude of e to the I theta, it's just 1 for any real value of theta. Any real number you plug in for theta, the magnitude of that complex number is just going to be 1. Furthermore, if you take some complex number e to the I theta and plot it on the complex plane and draw a line from the origin to that point, the angle between that line and the real axis is just theta. All right? So it turns out that complex exponentials are the natural way to write complex numbers in polar form. All right, now if I had sort of a real and imaginary representation, so I give you the vector a, b, where a is the real part and b is the imaginary part, you can say, oh, I can represent that analytically as just a plus ib, right? But if I gave you the polar representation of a complex number, you could write that analytically then as r e to the I theta, right? Because e to the I theta is a point where you draw that line, and that angle right there is theta with respect to the real axis, right? And then r is just the magnitude, right? If I take e to the I theta and multiply by r, I'm multiplying both real and imaginary by some number. So if this is length 1, this is just going to be length r, all right? R is in distance, that r is in real. Don't confuse them. Okay. Now, what can you do with a complex exponential? I'm going to show you. All right? There's just a myriad things that complex exponentials are helpful for, but just one of those is solving differential equations. Now, if you're listening to this presentation, I assume that you are in the physics major section, which means you're going to actually derive the wave equation, which means you need to know something about differential equations. So let's show you how complex exponentials can help you dealing with differential equations. And let's let you see what a differential equation is right here. So imagine I have a harmonic oscillator. Let's say I have some mass, and it's free to slide on a frictionless floor. Here's a wall over here, and let's say that the mass is connected to the wall by a spring. Now I take this mass, I move it over, and I let go. I want to understand what this mass is going to do with time. How's it going to move? Well, I know the force on the mass is just minus kx, Hooke's law, right? Where k is the spring constant of my spring. But I also know that force is equal to mass times acceleration. So putting those two together, the mass times the acceleration of my block is just minus kx. This is known as the equation of the motion of my block. All right? Now I just have to solve this. I have to find out what x is. But before I do that, there's a better form I can write this in, right? Because I remember acceleration is a function of x. All right? It turns out acceleration is the second derivative of x, right? The acceleration is the derivative of velocity with respect to time, and velocity is the derivative of position with respect to time. So acceleration is just the second derivative of x with respect to time. If we plug that in for acceleration, we get this equation here, the equation of motion for a simple harmonic oscillator. This equation is known as a differential equation because it has a derivative in it. Now, solving differential equations are kind of like solving integrals. First, you have to take a class in it, right, to understand what you're doing. And when you take that class, what you'll find is that there's all different kinds of them. Some of them are easy to solve. Some of them you can solve with one technique. Some you can solve with another. You have to learn a bunch of different techniques and learn when to use one versus another. And some of them you're just not going to be able to solve with any technique analytically, and you're going to have to go on a computer and solve it numerically. Differential equations are kind of like that. Now, I'm not going to teach you a lot of methods for solving differential equations. That's for another class. But it turns out this equation is simple enough that we can solve it by being clever. So what we're going to do is we're just going to look at it and see, what does it tell us? What does it tell us about what the solution should be? I'm going to divide both sides by m, and it'll maybe make this a little clearer. So if I divide both sides by m, I get second derivative of x with time is equal to minus k over m x. And I look at that equation, and what is it telling me? It's telling me if I take the second derivative of x with respect to time, I just get x back times a constant. So let's think, what functions can I take two derivatives of them and get the same function back times a constant? Well, I can think of three of them off the top of my head. Sine, cosine, cosine, and e to the something t. All right? So, we have some good guesses. Let's try one of our guesses and see if it works. So I'm going to guess that my solution is equal to a times sine of omega t plus phi. All right? So, I'm just saying, okay, I can take derivatives of this and the a just sits there and doesn't cause any trouble. So let's make our solution more general by throwing some constant out front, because I think that's going to work. All right? And this phase shift right here, phi, that allows me to kind of test both the sine and the cosine solution at once, because cosine is just sine shifted by 90 degrees. So if I go and I plug this into my equation and I find that, oh, this only works if phi is equal to 90 degrees, then I say, oh, the sine solution doesn't work, but the cosine does, right? Does that make sense? So I'm trying to be general here. Let's plug it in and see what happens. So my equation was, again, the second derivative of x with respect to time is equal to minus k over m times x. So I need the second derivative of this. I take the first derivative of x with respect to time, and I get, well, let's see, I get a, sine becomes cosine, but then I take the derivative of what's inside, and that brings out an omega. If I take the second derivative of x with respect to time, all right, my cosine becomes minus sine. I still have my amplitude, I still have my omega, but if I take the derivative of what's inside, that brings out another omega, and I get that. All right? So, plugging this into my equation, I find that minus omega squared a sine omega t plus phi is equal to minus k over m x, and x is a sine omega t plus phi. Now, if I can make this equation true somehow, then that means that this is a solution. So let's see if I can make this true. Well, first of all, the signs cancel out. That's nice. And the a cancels out. And I'm left, oh, and the minus sign cancels out. And I'm left with omega squared is equal to k over m. So if omega is equal to the square root of k over m, then this works. This is a solution. So it turns out it doesn't matter what a is, and it doesn't matter what phi is. All of it matters is that omega is the square root of k over m, and then this is a solution. And that's cool, right? I kind of expected intuitively that a should be some free parameter, because I can pull my mass out and let it go. I can pull it out a little bit, or I can pull it out a long ways. I had to be able to make this mass oscillate with big or small amplitude, right? And the phase just depends on, when I pull it out, right? Do I pull it out at time t equals 0? Do I pull it out sometime before time t equals 0? So you expect to be able to make it oscillate with any phase you want. So I wasn't surprised that these turned out to be free parameters. And it's also not surprising that omega is not a free parameter, right? That the oscillation frequency depended on the properties of the system, the spring constant and the mass. All right, so we found our solution. We can use it. It's got two free parameters. We've got two free parameters to plug into it, right? The initial position and the initial velocity of our mass. I can plug those in, find these parameters, whatever, and get the specific solution to describe the particular oscillation I'm looking at with my mass. But now let's consider the other potential solution that we ignored, the exponential one. Let's see what happens if I assume that x is equal to a e to the alpha t. Okay? Well, let's plug that into our equation. Well, to do that, I need the time derivatives, all right? I'm going to shorthand, if I put a dot over something, that means the first time derivative. And the first time derivative of this, right, I take the derivative of my exponential, it just brings the alpha down. So it's just alpha a e to the alpha t. The second time derivative, I'll use two dots to represent that. It just brings down another alpha. Alpha squared a e to the alpha t. All right? So I plug this into my equation, right, my differential equation. And the differential equation said that the second derivative, which is alpha squared a e to the alpha t, is equal to minus k over m x, which is a e to the alpha t. The exponentials cancel out, the a's cancel out, the minus sign does not cancel out. And we're left with alpha squared is equal to minus k over m, or alpha has to equal the square root of minus k over m. K is positive, m is positive, so this is like the square root of minus 1 times the square root of k over m. So this is, you can separate that out. The square root of minus 1 is just I. So this is I times the omega that we found before. So our solution ends up being a e to the I omega t. Groovy! This is the complex exponential that I told you was going to come up. Now, isn't this awesome? Now we have a solution which is an exponential. They're a lot easier to manipulate mathematically. But there's a problem. This solution describes a block which has a complex x-coordinate. It like moves into the imaginary plane. Real blocks don't do that. So you might think that this solution is useless. But remember, our solution can be written as a e to the I omega t. That can be written as a cosine omega t plus a I sine omega t. Sine omega t is a valid solution. Cosine omega t is a valid solution, right? So kind of our complex exponential kind of has two separate good solutions, but it's just kind of stacked them together by multiplying one of them by I. So what I'm going to do is I'm going to come back and say that's not really our solution. I'm going to call that x tilde, all right? Tilde, tilde, all right? This isn't really our solution. This is sort of a mathematical crutch. And I'm going to say my real solution, x, is, I could take the real or the imaginary part. Let's just take the imaginary part of x tilde. When I take the imaginary part, that's just a sine omega t, which I know is a good solution. So this is what we do oftentimes when we use complex exponentials to solve differential equations. We get this thing that is not realistic. It's complex, right? But then we say, if I take the real part of that, or if I take the imaginary part of that, that is a valid solution that describes a real thing happening in real space. But the complex exponentials are easier to manipulate. So I'm going to do all of my work with the complex exponentials, but then in the end, I'm just going to take the real part, or the imaginary part. I decide right up front. My solution is really the imaginary part of this, but I can manipulate it using the exponentials, which are easier, and then get my solution in the end by taking the imaginary part. All right, so exponentials, complex exponentials are really useful. Now, I could have just gone right to sine and cosine. That wasn't too hard, right? So why even bother with all of this? Well, the simple harmonic oscillator equation is a simple equation. The name is the giveaway, all right? What if things get more complicated? Maybe complex exponentials can help us with something more complicated. So what we're going to do now is consider a differential equation that is more complicated. This is a simple harmonic oscillator plus drag. All right, so here's mass times acceleration. Here's the force due to the spring. But now imagine that I want my block to not be sliding on a frictionless surface. Let's give it a little friction. And it's kind of a simplest way to model friction is just to say, well, let's throw a force which is proportional to the velocity of our block. If our block is sitting still, the friction doesn't do anything. But if it's moving, then the friction is going to oppose its motion. All right, so we're going to throw in a force which is proportional to the velocity but pointing in the opposite direction of velocity. So this constant here, gamma, is just a constant, all right, just something to model friction. And here we have the first derivative of x, which is the velocity. So let's try our sine solution. X is equal to a sine omega t plus phi. I take my derivatives and I plug it in and I say, great, second derivative is a sine, x is a sine, first derivative is a cosine. The sines don't cancel out anymore. This is not a solution. Got a problem. All right, but let's try x is equal to a e to the alpha t. Let's try some exponential and plug that in. All right, well, the first derivative with respect to time is just going to bring down an alpha. It's just alpha times a e to the alpha t, right? So it's just x with an extra alpha in front. The second derivative is just going to give me another factor of alpha. It's alpha squared x. So I plug those into my equation. I'm going to get mass times alpha squared x is equal to minus kx minus gamma alpha x, right? And the x's cancel, and I'm left with mass alpha squared is equal to minus k minus gamma alpha. If I can solve this for alpha and find what alpha needs to be, I can plug that in, and then I've got a solution to the simple harmonic oscillator with drag. All right? So I'm going to rewrite this equation on this next page. Let's write it. I've got mass alpha squared, but let's bring the other stuff to this side too. So it's going to be plus gamma alpha plus k equals 0. Let's look at that. Did I miss anything? Nope, looks good. So if I can make this equation true and find what alpha needs to be, I can find a solution to my differential equation. But this is just a quadratic equation. I can use the quadratic formula. Right? Just plugging this into the quadratic formula, I find that alpha is equal to minus gamma plus or minus the square root of gamma squared minus 4mk, all divided by 2m. All right? So let's look at this. All right? So basically this is minus gamma over 2m, and then I have plus or minus 1 over 2m square root of gamma squared minus 4mk. All right? Let us, if you don't mind, let's bring this inside the radical. Okay, so minus gamma over 2m plus or minus, and then we're going to have the square root of, we have to square it to bring it in, right? So that's gamma squared over 4m squared minus, oh, if I divide by 4m squared, this is just going to be k over m, right? So this is just gamma over 2m plus or minus the square root of gamma squared over 4m minus omega squared. All right? Now, if I assume, just looking at this, if I assume very small friction, so let's take the limit where there's just a little bit of friction and I expect my mass to oscillate back and forth and slowly slow down, right? If I assume gamma is small, this term is smaller than that one, and the argument to my square root is going to be negative. All right? So let's write it more apparently that way. Plus or minus I times the square root of omega squared minus gamma squared over 4m. So I look at this and I say, aha! My solution, if I plug this into my solution, x is equal to a e to the minus gamma over 2m plus or minus I square root of omega squared minus gamma squared over 4m, all this stuff, t. I can separate that out. A is equal to e to the minus gamma over 2m t times e to the plus or minus I square root of omega squared minus gamma squared over 4m. So I look at this and I say, well, look, this is just a decaying amplitude. This is a real exponential, not a complex one, right? So I have an amplitude which is decaying, and here is just that oscillating thing that we saw before, except the frequency is tweaked, all right? So by solving the equation this way, we were able to get a solution. Our solution, as we expected, it had a decaying amplitude. So our oscillating box its amplitude dies with time, but also we saw that adding friction dropped the frequency of the oscillation a little bit. All right? Now you could have taken the other extreme. You could have said, let's assume that the damping is really big, then this is real, and then you'd say, oh, the whole thing is real, you get no oscillations, the thing just goes and slowly approaches equilibrium. All right? You don't need to really understand the damped harmonic oscillator for what we're doing in this class. What I really wanted to show you is we took an equation that we couldn't solve using sines and cosines, and we solved it easily using exponentials. And so complex exponentials, they're awesome. All right? I hope you learn to love them and use them regularly.